So you sometimes see these graphical representations of these concepts. So here we see a reaction that is spontaneous, and we have the extent of the reaction and the delta G, the free energy on the left. So we have the reactants on the left. The y-axis is delta G. So the reactants are on the left. We have just reactants, and the products are on the right. So the extent of the reaction, if we proceed from pure products to pure reactants. Now, this would be the standard free energy of the reactants. This would be the standard free energy of the products. And delta G for the reaction, delta G standard, is the difference between these two. So that's the difference. Now, what happens if you proceed towards products? You start to use up reactants and you start to form products. And so you can calculate delta G based on the natural log of Q, which will get bigger. Q will increase as you go. You're forming more products, losing some reactants, and Q will start to get bigger and bigger. Now, what happens is Q gets bigger as you proceed, and the reaction, delta G, becomes less negative, becomes more positive, and so therefore less spontaneous. Now, oh, by the way, why do we know that this is spontaneous? Because when we go from reactants to products, the delta G for the reaction will be negative because the products are lower, so we're going down. So delta G for the reaction is negative. So that tells us it's spontaneous. I forgot to mention that. So we start to increase Q. The reaction becomes less and less spontaneous until we reach this minimum in the curve. At the minimum point, what can we say? Q equals K and delta G equals 0. Why? We're at equilibrium. This is the low point in this curve. And then if we proceed beyond that towards products, Q becomes greater than K. And at this point, this is where delta G changes its sign. From here all the way down to the minimum, delta G, products minus reactants, is negative, but it becomes less negative, less negative, less negative until we reach the minimum, and delta G is 0. If we proceed beyond that, the delta G, the free energy change, becomes more and more positive, and Q becomes greater than K. So at the minimum is where we're at equilibrium and delta G is 0. Now, here's the thing. The more, well, first of all, this is spontaneous, so the minimum is closer to the products than the reactants. If we're going from left to right, it's closer to the products than the reactants because it's spontaneous. It's product favored. But in this situation, we would achieve an equilibrium. But where this minimum occurs from one reaction or another, it could be to the left or right of this. And so if the reaction is very, very spontaneous, Q could be so large that the minimum is basically pure products. So when you have these reactions that don't really form an equilibrium, they just go to products. They have a minimum. Basically, this curve comes down, and the minimum is basically right there at the products. As the minimum shifts to the left, it's still spontaneous, but the equilibrium allows for some reactants to remain. Now, when you get to a non-spontaneous reaction, delta G for the reaction is positive. The products have a higher free energy than the reactant, so it's uphill for free energy. Delta G standard is greater than 0. That's how we know it's non-spontaneous in the forward direction. Now, if we start all the way at pure reactants, delta G may be, delta G will be spontaneous unless the minimum is right at pure reactants. If you have something that's no reaction and it doesn't even react a little bit to reach an equilibrium, then the minimum would be right here. But this graph shows that the minimum is not right at the left side of this graph at pure reactants. So when we start out with just pure reactants, delta G is negative and it's spontaneous. Q is less than K, delta G is negative. Even though the standard free energy is positive, delta G at this point is negative. So the reaction proceeds in the forward direction. Delta G increases, becomes less and less negative until we get to equilibrium. Now the equilibrium condition in this reaction, Q equals K and delta G equals 0, but look at it, it's on the left side. It's closer to reactants than products. So this tells us the equilibrium favors reactants. Mostly reactants, very few products. And if you proceed beyond this, you leave the equilibrium state and Q is greater than K and delta G gets more and more positive and less and less, or more and more non-spontaneous, I should say. So once again, the fact that this is the minimum is closer to pure reactants tells us that it favors reactants. At equilibrium, there's fewer products than reactants. The delta G standard is positive, so it is a non-spontaneous process. But depending on the location of this minimum, if it's away from pure reactants a little bit, that means that you set up a true equilibrium where there's some reactants and some products. If the minimum was over here right at pure reactants, like this curve came down, it hit a minimum right there, then it would be basically no reaction. We wouldn't even set up an equilibrium. So here is one more problem. So we have the equilibrium constant for this reaction is 0.113, and with a standard free energy change of 5.4. So what do these two things tell us? The K is less than 1, so at equilibrium it's mostly reactants, very few products. Delta G is positive. What does that tell us? In the forward direction, it's non-spontaneous. We do not expect the reaction to go towards products, or if it does, only a small ways, and then it will reach equilibrium. So let's say we have these initial pressures. NO2 is 0.122 atmospheres and N2O4 is 0.453 atmospheres. So let's calculate the delta G for this. So these are not standard conditions. Standard conditions would be 1 atmosphere for everything. So we have our equation. we have to calculate Q. So we plug in the values, and remember the partial pressure of NO2 is squared. So if we crunch the numbers, we get Q is 0.0329. That is less than K. So we're not at equilibrium. The reaction will proceed to the right and form more products to reach equilibrium. So we plug in our values here. Here's our standard delta G, RT natural log Q. We got the R, the conversion to kilojoules, temperature, and natural log of Q. And look what's going to happen here. The RT natural log Q is negative, and it's greater in magnitude than the standard delta G value. So this actually makes delta G under these conditions be spontaneous. The reaction is spontaneous because it's negative under these conditions. So this, I'm going to go back to this graph here. This kind of graph is what we've just seen. Delta G standard is positive. It is a non-spontaneous reaction. However, where we were in this graph was Q less than K, delta G is negative for those conditions. So the reaction proceeded until it reached equilibrium. So under those conditions, we calculated that delta G was negative under these non-standard conditions. The reaction would then proceed forward, and we would get to where we're at equilibrium. So the reaction we would not expect to go very far in the forward direction, but it will a small amount to reach equilibrium.